The next topic we're going to discuss is base number systems. This is section 4.3 from the textbook Math in Our World. So what is a base number system? These are numeration systems that use Hindu-Arabic numerals but use a different base than the Hindu-Arabic system. So if we use our regular numerals, so some combination of numerals 0 through 9, but we base the system on powers other than 10, this is called a base number system. Now we've seen one example that used a different base already. We've looked at the Babylonian numeration system, and they used a base 60. Now that wasn't a base number system because they had different numerals. They used cuneiform, those symbols for 10 and 1, rather than our Hindu-Arabic digits for 0 through 9. Alright, so here let's review expanded notation first before we look at a few examples. Alright, 453 in expanded notation. So we want to emphasize the powers of 10 that are behind this number. Alright, so this is 4 times 100 and 5 times 10 plus 3 ones. Then the final step is to write these using powers of 10. So this is 4 times 10 squared, 5 times 10 to the first, or just 10, and then 3 ones, or you can even just write 3. Okay, so this is expanded notation. Now this is going to be helpful for different bases, and you'll see why in a minute or two. Let's start out with the number 13 and write this in 3 different bases below: a base 10 system, a base 5 system, and a base 7. Alright, so you may want to use toothpicks or some sort of an object to have on hand if it helps you to picture this or to move objects around. I'm going to write out some tallies at the top here so that we can work with some actual symbols to represent 13. Alright, so I'm going to write out tallies. So there's 5, here's 10, and 13. Now to write this as a base 10 number is just to write this describing how many groups of 10 and how many ones left over. So it already is a base 10 number. And notice if I look at my grouping up top here, if I kind of, and if you're using toothpicks or something, if you shove 10 of those objects together, alright, and make a group, then notice you have 3 left over. So to write this as a base 10 number is just to write 1, 3, and that 1 represents one group of 10, and the 3 represents 3 ones. Okay, so that's the expanded form. Now, to write this as a base 5 number, I should have erased this first. Let me redo that real quick. Alright, so to write this as a base 5 number, I want to emphasize how many groups of 5 there are and how many ones left over. So now if I circle or push together groups of 5, notice that there are 2 groups of 5 with 3 ones left over. So as a base 5 number, I would write 2, 3, and I would put a little subscript, a tiny number 5, to show which base I'm in. So this representation, it kind of looks like our normal numerals, but it's a completely different way of writing this quantity of 13. And this is showing that there are 2 groups of 5 and 3 ones left over. Okay, that's grouping by 5s. And then finally 7s. In base 7, we want to show how many groups of 7 there are. So I can circle one group of 7, and then I have 6 left over. So in base 7, I would write 1, 6, and then a little tiny 7 to show that this is base 7. And this represents one group of 7 plus 6 ones. Alright, so 3 different representations, these 3 all for the same number. Now for base 10 numbers, we don't put a little tiny 10. 10 is our base, so we just assume that it's base 10 if you don't see anything there. Alright, let's try the number 20. So again, maybe it would be helpful to have some objects on hand. Okay, and then 1, 2, 3, 4, 5. There we go. That's 20. Okay, so in base 10, if I look at the groups of 10, here's a group of 10, and here's a group of 10. So I have enough to make 2 groups of 10 with no 1s left over. So 2, 0, and that means 2 groups of 10 with 0 1s left over. Alright, and that doesn't look any different than the normal way you're used to seeing 20 represented, and that's because we do use a base 10 system. Alright, how about base 5? So I would circle or group together groups of 5, and I have enough to make 4 groups of 5 with 0 1s left over. Okay, so I would write this 4, 0 with a little tiny 5, and this means 4 groups of 5 plus 0 1s. Okay, and you can check and work out that arithmetic to see that that is 20. And then finally base 7, I'll group 7s together. So here's 7, here's 7, and I have 6 left over. So this is enough to make 2 groups of 7 and 6 left over. Okay, subscript of 7. So this is 2 7s plus 6 1s, and if you check, 2 times 7 is 14, plus 6 does equal 20. Okay, so again, 3 different ways to write the same quantity, the same number of 20. Alright, and let's try one more example, the number 53. So we already know what this looks like as a base 10 number. So let's try writing this as a base 5, 7, and base 2 number. Okay, so this is a little bit larger of a number, so I won't write out all of the tallies. You may still choose to use toothpicks or something like that to count out 53 of those things. So let's just try to figure out what we would do here. All right, so in base 5, let's think about how many groups of 5 we have in 53. All right, and notice we have 10 groups of 5. Okay, so we have 10 5s and 3 1s. All right, but notice 10 is larger than a digit, so it would look a little bit weird to write like a 10 and then a 3. All right, that's a little bit confusing. So here's what we do instead. We actually group whenever we can make 5 of anything. All right, so think about in base 10. If we had the number 300, I wouldn't write that as 30, or let's do like 304. I wouldn't write that as 30 10s and 4 1s. I have enough to make 10 10s or hundreds, 3 groups of hundreds plus 4 1s. So anytime you have 10 1s, we group, and anytime we have 10 10s, we group into 10 squareds. Now we do the same thing in base 5. So anytime we have 5 5s or 25, we group again. Right? So this is the start of seeing how the place value is different in these different bases. Okay, in base 10, some of our first places are the hundreds, the 10s, and the 1s. But in base 5, we have groups of 25, that's 5 5s, groups of 5s, and groups of 1s. All right. So in 53, there are 2 groups of 25, and then there are 0 groups of 5 left after that, and then there are 3 1s. So that's the expanded form, and as a base 5 numeral, I would just write 2, 0, 3, base 5. All right, how about base 7? Well, in base 7, what's after 7s? Anytime I have 7 groups of 7s, we would group that and move that up to the next place value. So we have 7 squared is the next place value after 1s and 7s, right, or 49s. So in base 50, or the number 53 in base 7, we have 1 group of 49, 7 squared. Then we have 0 7s left over. Okay, because if you take away 49 from that, that leaves you with 4. So then there would be enough to make 4 ones left over. So in base 7, that would be 1, 0, 4, base 7. Okay. Now to write this in true expanded form, I should swap these out. I want to write these as powers of the base. So this would really be 5 squared, and this would be 7 squared. Okay, so expanded form, and then as a base 5 and base 7 numeral. Base 2, this is going to be the longest representation. We group by 2's. Okay, so in base 2, we have the 1's place, then the 2's place, then the 2 squared's place. All right, that's 4. 2 cubed is 8. 2 to the 4th is 16. We have a place for 2 to the 5th, or 32. And the next is 2 to the 6th, which is 64, and we would keep on going. Okay? So this is similar to ones, tens, hundreds, thousands, 10,000s, etc. We're just multiplying by 2's in this case. Alright, so in base 2, we have enough to make groups of 32, not enough to make 64's. How many groups of 32? We have enough to make one of those. One group of 32, or 2 to the 5th. Okay, and if you subtract 32 from 53, okay, that leaves you with 21. So not enough to make another group of 32, but certainly enough to make a group of 16. All right, and subtracting 16 from 21, that leaves 5 left over. So that's enough to make, oops, sorry, I should write 2 to the 4th. 2 to the 4th. All right, 5 left over. That's not enough to make a group of 8, so no 2/3, 2 to the 3rd. Okay, but I do have enough to make one group of 4. All right, or I should write that 2 squared. And then 5 minus 4 is 1, so that's not enough to make a group of 2, but it is enough to make a group of 1. Alright, so in base 2, I'm emphasizing powers of 2, and I would write this 1, 1, 0, 1, 0, 1, base 2. Alright, now we'll look at many other examples of these in the next couple of videos, but I just wanted to give you a few examples to show you an overview of how this works, writing the same number in different bases, so different representations, and then looking at expanded form for different bases as well. So similar to base 10, but now instead of powers of 10, we have powers of whatever the base is. You may also be wondering, well, why do we even use these bases? How did these start? Do they have any applications today? Why in the world are we studying this? So one reason, it's really emphasizing the value of place value and what that does for our number system. It's kind of broadening your knowledge of bases, what exactly that is. And then also we actually do use these bases in normal everyday applications. Time is one example that we've talked about. Time is sort of like a base 60 system. We roll things over at 60 and at 3600 for seconds into minutes and minutes into hours. All right, so when you see like 1 hour and 1 hour and 2 minutes and 5 seconds, right? You know that 1 hour is not 100 minutes. You know that it's 60 minutes. So you're working with base 60 at that time. Computers use base 2 and sometimes also base 8 and base 16. All right, and then if you're interested, there's a book, and let me write the title here. All right, there's a book called Zero, The Biography of a Dangerous Idea, and this is by Charles. Okay, I don't know how to pronounce this, maybe Seif or Seif, probably Seif. And it's a history of zero, but he also does discuss some origins for these base number systems and different ways of grouping other than 10, and also some current people groups that still use different bases. So not everyone is base 10. There are some tribes in South America and other regions of the world that still group by twos. For example, there's one tribe that likes to count with their hands, so they would, count with their hands as 2, and so rather than say 5, they might say in their language 2 and 2 and 1. And that's an example of kind of like a base 2 system, counting by twos. Another example is if you go back and look at the French words for numbers, okay, the number 80, rather than the way that we say that, 80, which kind of implies 8 tens, all right, 8 groups of 10, theirs can be traced back to words that mean 4 20s, all right, for 80, and then for 90 would be 4 20s and 10. So there's a suggestion that perhaps they counted by 20s, maybe for all 10 fingers and 10 toes, something like that. Okay, so that's just a brief glimpse into kind of the history of these base numeration systems. And if you're interested, maybe check out that book and do some additional reading to see some of the uses and applications today for different bases like that. All right, thank you for watching.